In this video, we're going to apply some of the things we learned about general functions to the special case of permutations. And the first one we're going to look at is what we know about invertible functions. So a permutation, you'll remember by definition, is a bijection from a set X to itself. And we know that every bijection is also an invertible function. So if f is a permutation, then f has an inverse, f to the power minus 1, and that is also a bijection, so it's also a permutation. So let's look at what we can say about two-row notations for inverse permutations. So I've written a definition here of what the two-row notation of a permutation looks like. Now if you have an invertible function f, then that function satisfies f of I is equal to j if and only if f inverse of j equals I. That's kind of the definition of what f inverse is. So if we think about what this tells us about two-row notation, if f of I is equal to j, then that means beneath I in the two-row notation for f, you find the number j. So this is what it would look like. Well, if f inverse is equal to of j is equal to I, then what that means for the two-row notation for f inverse is beneath j, you have to write I. So this is telling you that the two-row notation for f inverse looks like the two-row notation for f with the top row and the bottom row swapped over, and then we have to reorder the columns so the top row of the two-row notation for f inverse is just 1, 2, 3 in the correct order. So let's try doing that in some examples. I've taken down here f, a permutation of the set 1, 2, 3, so an element of the symmetric group S3, and we're going to find the inverse for f. So we have to do that first of all by swapping the top row and the bottom row of the two-row notation, and then reordering so that the top row is in the correct order. So if we work out f inverse, well, if I swap the two rows and then reorder them, then beneath 1 I should have 1, beneath 2 I should have 3, and beneath 3 I should have 2. Okay, so that's interesting because in this case f inverse and f turned out to be the same. But that's not always true. So let's look at an example where g and g inverse are different. So here g is a permutation in S3. And to get g inverse, first of all I have to swap the two rows of the two-row notation. So I would have 2, 3, 1, 1, 2, 3, and then reorder the columns so that the top row is 1, 2, 3. So if I just reorder those columns, then g inverse I would have 1, 3 as the first column, 2, 1 as the next column, and 3, 2 as the final column. And this time g and g inverse were genuinely different because you can see that g of 1 was 2, but g inverse of 1 was 3. So this is not the same as g. Okay, in summary, finding inverses of permutations given in two-row notation is really easy. You just swap the two rows and then you reorder the columns so that the top row looks like 1, 2, 3 up to n. Okay, next fact about permutations, which comes from what we learned about functions, is that the composition of two bijections is a bijection. So if you look back to lecture 10b or video 10b, you'll find we did that in video 10b. So that means if I compose two permutations, the result is again a permutation. And this is really the interesting thing about permutations. This is when permutations start to get very interesting. So let's look at an example of composing two permutations and getting another permutation. So we're going to take f to be this permutation, it's an element of S3, and g to be this permutation here, again it's an element of S3, and we're going to work out f composed with g. So you'll remember that f composed with g is the function whose rule is first do G and then do F. And specifically what we're going to work out is the two-row notation for F composed with G. And to work out that two-row notation, well, beneath 1 I've got to write F of G of 1. So let's just work out F of G of 1. Okay, that's F of G of 1. G of 1 is 1, looking at this column here. So this is F of 1. And F of 1 is 2, looking at this column here. So F composed with G, with the input 1, has output 2. So I should write a 2 here. And similarly, if I want to know what F composed with G at 2 is, then I have to work out F of G of 2. And that is, well, G of 2 is 3. We get that from looking at the second column of the two-row notation for G. So this is F of 3, and F of 3 is 3, just looking at that last column of the two-row notation for F. So I need to write a 3 here. And F of G of 3, well, I could work this out, but actually I know what the answer is going to be, because remember a couple of videos ago we made the observation that if you have a permutation of 1, 2, 3 up to n, then the bottom row of the two-row notation for that permutation must be the numbers 1, 2, 3 up to n in some order. So I've got to have the number 1 somewhere on the bottom row of this permutation F composed with G. And since I haven't had the number 1 yet, well, it must be that the number 1 appears in that last column. Well, let's check, okay? Let's just check to see if I haven't made a mistake somewhere. F of G of 3 is F of 2, because G of 3 is equal to 2, as you can see by looking at the last column of the two-row notation for G. And F of 2, looking at the middle column for the two-row notation of F, is 1. Okay, so that really did turn out correctly. We really do have F of G of 3 is 1. Now, in general, when we talk about composition of permutations, we'll often talk about composition as if it were multiplication of real numbers. So, for example, we'll write Fg instead of F circle G, and we'll call it the product of F and G and not the composition of F and G. And the reason we do that is because it turns out that composing permutations is a lot like multiplying non-zero real numbers. For example, if you were multiplying real numbers, then x times y times z would be the same as x times y times z. Multiplication of real numbers is associative, just as composition of functions is also associative. And similarly, if you have a real number x, then it has a multiplicative inverse, x to the minus 1. And when you multiply x and x to the minus 1, you get 1. And very similarly, every permutation has an inverse function, which we write using a very similar notation to this. And when you compose a permutation with its inverse, you get the identity function. And the identity function behaves with respect to composition, just like the number 1 behaves with respect to multiplication. So in order that we can use the skills we already have for doing algebraic manipulation of multiplication and transfer those skills into the land of permutations, we'll very often use language which is very similar to the language we use when we talk about multiplying real numbers, when we're talking about composition of functions. Most importantly, I'll talk about multiplying permutations or forming the product of two permutations, when what I mean is the composition of two permutations. Okay, moving on. Let's look at a way in which composition of permutations is actually different to multiplication of real numbers. And that is that multiplying real numbers is commutative. If you have two real numbers x and y, x times y is always equal to y times x. But if you have two permutations, f and g, then f composed with g and g composed with f are, in general, not always, but in general, different. So let's see an example of that. Here are two permutations f and g, which are elements of the symmetric group S3. And we've already worked out F composed with G. And in fact, the answer we got was that F composed with G had the two-row notation, which I've written over here. Let's now work out G composed with F. So G composed with F of 1 is G of F of 1, which is G of 2, which is 3. So I put a 3 there in the two-row notation for G composed with F. Similarly, if we want G composed with F at 2, that's G of F of 2, which is G of 1, which is 1. So we put a 1 here. And again, using our observation that the bottom row of the two-row notation for a permutation of the set 1, 2, 3 up to n must be the numbers 1, 2, 3 up to n in some order. Well, I must have a 2 here, because somewhere on the bottom row there's got to be a 2. And since I've only got one space left, the 2's got to go there. All right, well anyway, the point that you can see very clearly here is that F composed with G in our example was not the same as G composed with F. That means composition of permutations is not in general commutative, and you have to be careful about the order in which you compose permutations. And a place where the order turns out to be very important is when thinking about the inverse of a composition. So again, in lecture 10, one of the things we learned was that if you have the composition of two invertible functions is again invertible, and the inverse of F composed with G is the inverse of G composed with the inverse of F. Right? So the order changes. You will remember our shoes and socks example for convincing you why the order had to change. So this is important because this is not F inverse composed with G inverse. Right? The inverse of F composed with G is G inverse composed with F inverse, not F inverse composed with G inverse. This is important because, as you've just seen, the order in which you compose permutations matters.